Welcome to Monmouth. Welcome to the first event of the 2023 Climate Crisis Teach-In. I am Catherine Duckett, Associate Dean of the School of Science and the fairy godmother of the Climate Crisis Teach-In. The Climate Crisis Teach-In is meant to raise awareness of both climate impacts and climate solutions so that you can help yourself and other creatures have a better life by investigating solutions or by advocating for climate solutions. Today, we have a fantastic lineup. We're going to have two presentations, more or less factual scientific presentations about sea level rise causes, sea level rise in more near term, about 30 years, and then a discussion of impacts on the coast with Professor Gina McKeever from the Kislak Real Estate Institute. And I'll begin by introducing Professors Paccico and Herrington, who are going to be our first two speakers. When we move to the panel, I will introduce Dr. McKeever. Okay? Wonderful. All right. Professor Matt Paccico in the gray is an adjunct professor here at Monmouth. He is also a staff engineer at Carollo Engineers, where he designs flood resilient infrastructure for coastal communities. Matt's focus is on helping coastal communities understand the rapidly changing and inherently uncertain science of ice sheet dynamics, which leads to sea level rise and sea level rise, to prioritize public investment and build long-term climate resilience at the local level. So coming back to the solutions that I talked about. Prior to joining the engineering field, Matt earned a bachelor's degree in chemical engineering and in environmental science from University of Rochester, where he also investigated the last ice age transition and associated sea level rises with their paleoclimate research group. He went on to earn a master's degree in urban infrastructure systems from New York University. And Tom Herrington, Dr. Herrington, is the Associate Director of the Urban Coast Institute at Monmouth University and serves as the New Jersey Sea Grant Consortium Resilient Communities and Economies Specialist. Tom has over 30 years experience in coastal resilience and hazard mitigation research, including monitoring and analysis of coastal system changes to storm surge and wave impacts. You guys remember Hurricane Sandy, and the analysis of nature and nature-based features for ecosystem restoration and community resilience. Prior to joining Monmouth, Dr. Herrington was the director of the Ocean Engineering Graduate Program at Stevens Institute of Technology and the director of New Jersey Coastal Protection Assistance Services. Dr. Herrington has earned 3 degrees from Stevens Institute of Technology, Bachelor of Degrees in Civil Engineering and an MS and PhD in Ocean Engineering. Dr. Paccico? Professor Paccico.
Thank you.
Dr. Herrington.
Good evening, everyone. Thanks for coming. As Dr. Duckett mentioned, I am Professor Matt Paccico, here to talk to you about sea level rise, focusing on long-term impacts specifically related to ice sheet dynamics. Dr. Herrington will take us through shorter-term impacts, and looking forward to the discussion with Dr. McKeever. So, why are we all here? If I can get this to work, maybe not. Let's see. Okay, we are all here. Well, we're all here because the Earth is warming. We are all aware that the Earth is warming. If you are not aware of that, probably not in this room. But generally speaking, when we talk about modern global warming, we're talking about the fact that temperatures have increased worldwide over the last 200, 250 years or so. We know why this is happening. This is due to increases in greenhouse gas concentrations. Those greenhouse gas concentrations are coming from human use of fossil fuels, human energy use more broadly. And this has wide-ranging effects, changing precipitation patterns, shifting crop regions, extreme weather events, and of course, what we're here to talk about today, sea level rise, just to name a few. But I want to start out by talking about the history of sea level rise really over the history of the Earth. Many people may not be aware that sea levels have varied significantly over the history of the Earth, tied directly to the amount of ice stored in polar ice caps and mountain glaciers. So this figure on your right is showing both the southern extent of glacial ice 20,000 years ago and the associated coastline, as well as the landward limit of the sea in the past 5,000 years in the Pleistocene era. And what this is showing you is that there is significant variation in the coastline, specifically of eastern North America, depending on where and how much ice is trapped in the polar ice caps. Why is this the case? Because the water that fills our oceans is the same water that gets trapped in ice. So the more ice that's trapped on the North and South Pole, what we'll talk about, the less water is available to the oceans, the ocean level recedes, and vice versa. This figure on the bottom here is showing you Florida, which is an excellent example because of how flat Florida is. Within the last 5 million years or so, Florida has looked like this, and as we know it today, of course. The coastline of Florida has shrunk 100 miles in the last 20,000 years, and we came out of the last ice age into the current, what we call interglacial period. But of course, while sea level has varied significantly over the history of the Earth, it has not varied significantly over the history of human civilization. In fact, if you look here, this figure is showing years before present, so today would be on the far right. Sea level has been remarkably consistent over what can be considered the entirety of human civilization, the last 5, 6, 7, 8,000 years. Humans have never dealt with this concept of sea level rise. We built cities on the coast, we built communities on the coast, settled there because it was convenient for trade, for food. We've never had to deal with this issue of changing coastlines, this issue of sea level rise until about the last 150 years. The last 150 years, we have seen worldwide unequivocal sea level rise, accelerating specifically in the last 20 years. And we know this through methods that Dr. Herrington is going to get into. We know this because we have reliable tide gauge measurements in many locations worldwide, some of which have been taking data for more than 100 years. In fact, we'll talk about the tide gauge that's just up here in Sandy Hook, New Jersey, that's been taking measurements daily, hourly of the sea level going back into the 1930s. So we have very solid record keeping of sea level rise. We've been able to supplement that record with satellite data, specifically in the last 20 years. And we can say unequivocally all over the world that global sea level is increasing. So we talked briefly about the relationship between sea level rise and this concept of ice that's stored on the poles. But let's look very specifically at the causes of current sea level rise. And these are rough numbers mainly used to communicate the ideas. There's two sources of what we call global sea level rise. These are sources of sea level rise that raise water levels across the globe uniformly. They are land ice melt and thermal expansion. We'll talk about both of those in a minute. And then there's also this concept of relative sea level rise. This concept that due to local land motion primarily, sea level doesn't rise everywhere equally. And what I'm showing you here in this figure is what we call glacial rebound. This is the concept that as the massive ice sheet that covered much of North America 20,000 years ago has receded, the land that was underneath that ice sheet that was compressed by that huge weight is slowly increasing, decompressing, and raising the level of the land here in red. And like a seesaw, the rest of the continental plate is sinking in the blue. And this little red dot here shows that Sandy Hook tide gauge that we'll talk about, very strongly sat right in that blue area. The tide gauge registers vertical land motion somewhere between 1 and 2 millimeters a year down. So the land is sinking and the sea level is rising. That compounds the effect of these global sources of sea level rise. So, talking about global sea level rise, we mentioned ice melt, which we will certainly talk about. But first, I want to bring up this concept of thermal expansion. Thermal expansion is a concept that I think is not at the forefront of people's mind when they think about sea level rise, but has contributed a third of sea level rise that we have observed to date, roughly speaking. And this concept of thermal expansion really is quite simple. Water expands when heated. The density of water decreases as the temperature of water increases. And it might seem like a small factor, but when you slightly decrease the density of water over the entire ocean column, it becomes measurable. And also worth considering, we said at the first slide that the Earth is warming. We're all familiar with the concept that global air temperatures are getting warmer, the effects of that. However, this figure here is showing that in reality, about 90% of that additional greenhouse heat that we're responsible for is absorbed by our ocean. So this little red bar down here at the bottom is the combination of all the heat added to the land, to the atmosphere, and to the ice. And this big blue bar here shows you how much heat we add to our oceans. We add so much heat to our oceans that it's enough energy to boil off Lake Ontario completely twice a year. Or if you want another metaphor, it's about equivalent to a nuclear bomb every 10 seconds or so going off in the ocean. That's how much energy we are adding to our oceans due to this excess greenhouse heat. So all that heat, again, contributes to very small density differences, but compounded across the entire water column makes a significant difference. That's a third of sea level rise that we've observed so far. But of course, when we talk about sea level rise, when we think about sea level rise, we think about melting ice, right? We think about how icebergs cave off, adding water to the oceans. When ice melts, specifically land ice melts, you're adding water to the oceans. You're filling the bathtub, the water level of your oceans rises. There are really four sources of land ice melt, and I've specified land ice melt twice now because it's worth noting that water that's already in, ice that's already in the water, sea ice around the North Pole, for example, does not contribute to sea level rise when it melts. That's like taking a glass of ice water on your table. The ice is already in the water. When the ice melts, the level doesn't rise. What we're talking about here is the equivalent of holding a handful of ice above your glass of water. As that ice melts, it drips down into your cup and absolutely will rise, cause the level of your glass to rise. So like I said, four sources of land ice melt that we see today. Mountain glaciers, these are small in the context of Greenland and Antarctica, small glaciers that are trapped typically at high elevation in the mountains. They are very quick to respond to climate change. There is a lot less volume of ice, which allows those glaciers to unfortunately melt faster. Mountain glaciers lose approximately 270 billion tons of ice a year to our oceans. And then you have really what you think about when you think about sea level rise, the Greenland and Antarctic ice sheets. I like these two images on the left because they are to scale. They give you a sense of the extent of these two ice sheets that you don't get from looking at a traditional map. A traditional map will extort the size of Greenland and spread Antarctica out along the bottom. You can see here, for example, that the area of Antarctica is actually larger than the area of the US. A lot of ice that's trapped up in these places. The ice sheets in Greenland and Antarctica range from a mile to 2 to 2.5 miles thick. So it's a lot of ice that we're talking about here. If you were to melt the Greenland ice sheet, you would add about 24 feet to global sea level rise. If you were to melt the West Antarctic ice sheet, about 12 feet of sea level rise. And if you were to melt the absolutely massive East Antarctic ice sheet in its entirety, you would add about 200 feet of sea level rise. The Antarctic ice sheets are two very distinct ice sheets: West Antarctic ice sheet, East Antarctic ice sheet. The East Antarctic ice sheet hasn't fully melted in at least 1 million years. The West Antarctic ice sheet is of significantly more concern. It is considered high risk. We'll talk about it more later. But that 200 feet of sea level rise, the East Antarctic ice sheet, not really something that we're extremely concerned about right now. Something that we keep an eye on to make sure that we're not misunderstanding the dynamics of that ice sheet, but significantly colder, significantly more stable. This ice sheet, the East Antarctic ice sheet, adds ice just about as often as it loses ice year to year. The West Antarctic ice sheet is where you see ice loss and the potential for a real significant catastrophic sea level rise. So now I want to look at what we've observed so far. This is from that Sandy Hook tide gauge. Remember, I said that there's about 90 years worth of continuous measurements. So I just went online, downloaded all of that data, took monthly averages and threw them on a figure. And you can see pretty unequivocally that the sea level at that tide gauge is rising. There's very clearly a trend upward from the baseline when the record started. We're currently well over a foot above where we were when those records started. What's harder to see is that there's really a couple different trends in here. If you take the trend from the 1930s to the year 2000, the average is about 1.4 inches per decade, or 0.14 inches a year of sea level rise on average. However, if you look at just the last 20 years, the average is about 4.5 inches per decade. We've seen significant increase in the rate of sea level rise and in the rate of vertical land motion. And again, that 2010 average is about 1.4 feet, almost 1.5 feet above where we were when records began. So we've already seen well over a foot of sea level rise in this part of New Jersey, just up the road. And again, you can do this for any number of tide gauges around the country. There's dozens of them that are run by the federal government, by NOAA, the National Oceanic and Atmospheric Administration, and they will all show you about the same thing. All will show you general sea level rise, varying degrees, again, based on that vertical land motion component, but general sea level rise over the last 100 years. And again, not only sea level rise, not only is sea level increasing, but the rate of increase is increasing. So the obvious question, now that we understand sea level rise, we've observed sea level rise, is where are we headed? Well, unfortunately, the answer is not that simple. Like we said, current sea level rise, modern sea level rise, has been dictated by human activity. So it's impossible to know where we're going to end up if we don't know how much humans are going to warm the planet between now and, say, the end of the century, right? Currently, we've warmed the planet on average about 1.1 degrees Celsius. This is what the world would look like at 1.5, 2, or 4. This is considered an extremely optimistic scenario. 2 degrees is considered a scenario that we would very much like to achieve. Beyond 2 degrees, we think that there are potential catastrophic consequences of climate change beyond sea level rise. And 4 degrees is generally the thinking of the upper limit business as usual scenario today. So how can I tell you how much sea level rise is going to happen by the end of the century if you can't tell me how much we're collectively going to warm the planet by then? Make sense? But we can look at what we could expect if we act sooner rather than later. We can look at what we could expect if we decide collectively to not take action And so what this is showing is different emission scenarios, different warming scenarios. So if the Earth warms closer to 4 degrees, you get these red lines up here. If the Earth warms closer to a degree, degree and a half, you get these lines down here, that blue. And so we're looking, say, at the end of the century, we can sort of create an upper and lower bound of expected sea level rise. And now, again, this is global sea level rise. So this is not taking into account that vertical land motion, which we said is a detriment to us here in New Jersey. But we can say that there's a upper and lower bound 1 to 3 feet of sea level rise by 2100 that is dependent on warming. Now that 1 foot, as Dr. Herrington will get into, is probably ridiculously optimistic. We expect to see 1 foot significantly sooner than that. 3 feet possible by the year 2100. Again, strictly based on how much we warm the Earth. But then there are these 2 dotted lines, and I apologize if those are hard to see. These 2 dotted lines up here, which the IPCC, the Intergovernmental Panel on Climate Change, refers to as low confidence scenarios. Scenarios that are not understood completely, that could contribute to significant sea level rise, especially looking out toward the end of the century. And you can see here that these low confidence scenarios, whoop, what did I do? These low confidence scenarios call for as much as 4.5 up to 6.5 feet of sea level rise globally by the year 2100. So what are those low confidence scenarios? Those low confidence scenarios represent us crossing what we call tipping points. These are periods, dramatic shifts in the rate of sea level rise, essentially a paradigm shift in how sea level rise is occurring. So we talked earlier that sea level rise currently is 1/3 thermal expansion, 2/3 ice melt. This would represent a significant change in one of those 2 variables, really the ice melt. And we have seen evidence of multiple tipping points in the record of the last glacial interglacial transition. So we saw all the way back on one of the first slides that the sea level in Florida was 390 feet lower than it is today during the peak of the last glacial period. So that's down here, the last ice age, the peak of the last ice age. And you see these 3 inflection points, where if you're standing on the precipice of one of these inflection points and you're using the past to dictate the future, you're going to severely underestimate sea level rise. And so these tipping points exist. We know they exist. We have records of tipping points, not just for the last ice age transition, but ice age transitions going back further. And so what tipping points are we concerned about today? There's 2 that I'm going to talk to you about. The first one is the Greenland ice sheet, or GIS tipping point. This is the point where we have warmed the Earth enough that the Greenland ice sheet will melt in its entirety. The question just becomes how long that process takes, right? So this is the point where we lose control to limit ice melt. We lose the control to limit sea level rise. We have committed to that full 24 feet of sea level rise. The only question is how long that takes. And our current understanding is that that will take quite some time to fully melt, on the order of 1,000, 2,000 years to fully melt. But it is worth keeping in mind that it will actively add to sea level rise for that entire period, right? So it's not just, oh, it's 2,000 years in the future, we don't have to worry about it. We're talking about the point where we potentially lose control of sea level rise. And a paper that was published at the end of last year was the first effort to really dig down deep into these tipping points and see at what level we have crossed them. And they came up with the best estimate, 1.6 degrees Celsius. At 1.6 degrees Celsius, it is likely that we have lost control of our ability to limit the Greenland ice sheet from fully collapsing. Again, we've already warmed the Earth 1.1. We expect to get to 1.5 potentially in the next couple of decades. And so, like I said, these tipping points represent a shift in how these ice sheets melt, a shift in the rate at which they melt, a shift in the dynamics that cause their melt. And we're already seeing potentially worrying signs that the dynamics on the Greenland ice sheet are changing, right? So in 2012, the first time in recorded history on the Greenland ice sheet, that summer was the first time that the entire ice sheet, every square inch of it, melted for some point over the course of the summer. First time in recorded history that happened. It happened again in 2019. 2021 had a 95% melt extent. So we went from melt extents, up here you're talking melt extents of 40, 50, 60% over the course of the summer to now 2, almost 3 times in the last 10 years, a full melt extent on the Greenland ice sheet. We expect that at a minimum, the Greenland ice sheet's collapse will add 5 to 10 inches of sea level rise by the year 2100. However, as you can see here, these years of full melt extents cause significant drops in the amount of mass on the Greenland ice sheet. If 2012, 2019 becomes more of the standard year, we could see as much as 30 inches of sea level rise from the Greenland ice sheet. Again, we don't think that that's a extremely likely scenario to happen, but we're seeing trends in the wrong direction. This is the low confidence part of those low confidence scenarios. We don't fully understand at what point we have lost control of the Greenland ice sheet, and we don't understand what that transition looks like from this side of the tipping point to that side of the tipping point. The other tipping point that I want to talk to you about is the Thwaites Glacier. This is a diagram of Antarctica. We looked at Antarctica earlier. This is the mountains that divide East and West Antarctica. And sticking out right over here on the Amundsen Sea is the Thwaites Glacier. It is theorized that the Thwaites Glacier in West Antarctica is physically supporting, bracing the rest of the West Antarctic ice sheet. And so the saying goes, if Thwaites goes, waste goes. So there's 2 feet of sea level rise in the Thwaites Glacier. There's 8 feet of sea level rise in the rest of the West Antarctic ice sheet. Again, rough numbers. And our best estimate for this tipping point, 1.5 degrees Celsius. At 1.5 degrees Celsius, we think that we've probably lost control of the West Antarctic ice sheet. We can no longer limit that. We are committed to 12 feet of sea level rise. Again, it's a question of how long that takes. We're more concerned about the Thwaites Glacier than we are about the Greenland ice sheet collapse for reasons that we'll get into. We think that the Thwaites Glacier collapse is on the order of potentially a couple hundred years, potentially quicker than that. Again, for that full 12 feet of sea level rise. And I know a couple hundred years sounds like a long time. It's certainly beyond our lifetimes. But 12 feet of sea level rise will significantly remake the coastlines. So whatever humans plan on being around at the point that this whole thing melts, will have a hard time adapting if we don't help them out. So why are we so concerned about the Thwaites Glacier? The Thwaites Glacier and much of the West Antarctic ice sheet sits on land that is actually below sea level. The land slopes down, as you can see in this diagram, away from the ocean. And so as the ocean warms, remember we said that 90% of greenhouse heat, additional greenhouse heat, is absorbed by our oceans. All of that heat is starting to cut away at the bottom of this glacier. and destabilize it from below while it's thinning from above. And the way these glaciers work is that they slowly flow out to the sea. When they're stable, they're replaced with ice on the back as they lose ice on the front to the ocean. But what's happening now is these glaciers are thinning and they're picking up speed as they collapse into the ocean. A recent study that parked themselves on the ice shelf, which is this part that overhangs the glacier, dropped the probe down into the water and found that the ocean current that was cutting away underneath the ice was about 40 degrees Fahrenheit, which is significantly warmer than expectations and is certainly warm enough to contribute significantly to the collapse of these glaciers.
Is that Fahrenheit or Celsius?
40?
4 degrees or?
Oh, 4D, sorry, 40 Fahrenheit.
Oh, Fahrenheit, okay,
Yes.
yes, it's significantly above freezing.
40 Celsius also significantly above freezing.
Celsius also above freezing.
So this is satellite data of the Thwaites Glacier showing the ice flow and the elevation change. So the edges of the glacier here and this glacier next to it, the Pine Glacier, which we're also concerned about, showing how these glaciers are losing significant mass every year. About a meter of ice is lost every year. And also these glaciers are accelerating toward the ocean, especially accelerating at that part that sticks out into the ocean, which we call the tongue. That is causing significant stress on the back end of these glaciers, which has led to fractures in the ice. All of these discoveries that have been made in the last couple of years about just what's happening on these ice sheets. There is a group of scientists that was planning in 2019 to go to the Thwaites Glacier. Their trip got delayed till 2020 and then COVID hit, so they didn't actually get there until 2022. By the time 2022 rolled around, they couldn't use the field location that they had originally set up because there were fractures and cracks in the ice and they didn't deem it stable enough for humans to camp there for a couple of weeks. So these things are changing quickly and our understanding of them is changing quickly. So again, let's bring it back to New Jersey, where we're heading. This is that data that I showed you earlier from Sandy Hook. And what I'm showing you here are the National Oceanic and Atmospheric Administration's projections to the end of the century. They have a scenario with moderate warming and none of these additional ice sheet processes contributing significantly. And then they have scenarios with increasing levels primarily of West Antarctic ice sheet collapse. And when you combine that with expected vertical land motion here in New Jersey, you see that in total, starting from our 1930s baseline, we can expect a minimum of 3 feet of sea level rise by the end of the century, upwards of 5, 6, 7, 8 feet, depending on these processes that we don't fully understand.
Low confidence means not low confidence that it will happen, but low confidence in our understanding of how it would happen, right?
It's a little bit of both. We think that, like I said, we think that these full collapse scenarios are potentially hundreds or thousands of years out. But like I mentioned here, these changes are not going to be linear. So what that curve looks like, we're not 100% sure. And how those ice sheets slowly or quickly collapse, again, not 100% sure.
Thank you.
And with that, I'll turn it over to Dr. Herrington.
So thank you. So we've seen that we rely on our observations of water levels and tide gauges pretty significantly in how we project what may happen in the future, right? So the basis of our projections are what we've observed and what we can model based on those observations. So I wanted to do a little bit more localized deep dive into the data we look at tide gauges and what it tells us not only about sea level, but what we could expect to happen as sea level rises. So sea level, if you think about it, is just the playing field on which all the other processes are continually playing out on. So the storms that come up our coast are still going to come up our coast. They're still going to create storm surge. We're still going to get rainfall at high tide. And sea level is going to affect all those processes. So this may be a little dated, but this is NOAA's water level observing network. It's probably hard to see, but all these little triangles are where we have a NOAA tide station. Some of them have been in for more than a century, as Pat had mentioned. Some of them are younger than that. But all this data is collected and maintained and analyzed by NOAA for use in a number of different products. And nothing left.
No, you're right.
Right. Or can I push the button? All right, I can just leave. Maybe not. Nope. All right, thanks. All right, good. So here in New Jersey, this didn't come out too well, but these pins mark where we have water level monitoring stations. Particularly here, we have one up in New York at the Battery, Lower Manhattan. We have one at Sandy Hook that Matt mentioned. We have one in Atlantic City, and we have one in Cape May. They're primarily the ones we look at for coastal water level variation. This is the picture of the station at Sandy Hook. It's been measuring data since 1910, so over a century. Here is the Atlantic City gauge. It's actually on the steel pier in the ocean. Very rare to find one of these gauges in the ocean itself, not in a bay or an estuary. And that's been in since 1911. So these are very significant data sets for us to look at. These stations can measure, they measure every 6 minutes right now. So they're collecting data in 6 minutes, and they're taking that data and storing it. They have a record so long they can predict the tide. I'll talk a little bit about that in a second. We can have tidal predictions at these locations. And then we can see how the observed water levels are varying compared to the predictions. This is the predicted tide in Atlantic City from January, no, October of last year. And there's a couple of things that stick out when we look at what the predicted tide is. And one is we see this variation in tidal range, the difference between high water and low water on a daily basis. And we see some time periods during the month, we have higher ranges of tide. And in other periods, we have lower ranges of tide. And so this is what we term the astronomical tide, because it's completely driven by the location of the Earth, Moon, and Sun relative to each other. And so this is a gravitational attraction. So the ocean is liquid, so it's pulled away from the Earth by the Moon and the Sun. The Moon is predominantly the #1 tidal forcing constituent. And when the Earth, Moon, and Sun are aligned, so they're on the same plane, we have what we term spring tides, where we have the higher ranges of tides during the month. And then when we have the Earth, Moon, and Sun at 90 degrees each other, we have the lower tidal ranges of the month, and we call those neap tides. Spring tides is kind of a misnomer. It's not that they only occur in the spring. It's because the added tidal range caused boaters to put extra lines on their boats called spring lines to keep the boats in place. So we have the predicted tide, but we're also observing water levels at these stations every 6 minutes. And the blue line here is that astronomically predicted tide for October of last year. And this green line is the actual observed water level. And so we can see that on a day-to-day basis, the predicted tide isn't a good indicator of what the actual tide may be. And so there are these variations in here around what we expect the tide to be that create noise in the record, right? So we're thinking about things like sea level rise, 4 millimeters per year. that's in the noise of this signal of observed water level. So how do we get rid of that so we can figure out what sea level is actually doing? So I want to focus in here just on this first week or 5 days of October of last year and talk a little bit about what we're seeing in the observations. So again, the blue line is the predicted water levels based on the position of the Earth, Moon, and Sun. The green line is the observed water levels that were taken at the station. The difference between the predicted water elevation and the observed elevation is what we call storm surge. So this is the added water in the ocean above the predicted tide due to some meteorological condition. Then the green tide, the observed line also is termed the predicted meteorological, not predicted tide, the meteorological tide. So this tells us that this added water is actually due to the weather or meteorology. And many times you also hear it referred to as total water level, which includes the predicted tide plus the storm surge. So we know a lot of things from observing the tides for more than a century, actually longer than that in some places. We certainly know that we see the tide variation due to this Earth, Moon, Sun gravitational attraction. We know very well where those three things are going to be at any given time in space and time. So we know we can use these relative positions and their gravitational attraction to predict the tides. And when we do that, we have a good confidence in being able to say, hey, when is it going to be higher than tide? When should we bring our boats out or not out? But we also know weather generates variations in the predicted tide, and that creates noise in the signal, right? So in order to determine things like sea level rise or changes in the elevation of sea level, we need to filter these meteorological tides out in some way, and also make sure that we capture the full range of locations of the Earth, Moon, and Sun in the space. So how long do we have to average this record to remove all these variations and understand what the predicted tide should be? So it turns out this is a little bit more of a schematic of how the Earth, Moon, and Sun appear relative to each other. A number of things happen here. One is that the Earth's tilted on its axis. And so as it goes around the Sun, the tilt changes one side to the other. So we get seasonal changes in heating of the Earth and the tide. We know that the Moon orbits the Earth at an angle, and that ranges of about 28 degrees on either side of the equator. So we have the Moon varying in its position around the equator as it goes around the Earth, and the Earth is going around this elliptic orbit. And if this was the instantaneous position of the Earth, Moon, and Sun right now, it would take 18.6 years for them to get back to the same exact position. And so that's a long time to average a record, right? So in order to make sure that we're capturing all the possible gravitational tidal elements at that station, we need to average over 20-year increments on this, right? And so I like this spot. This is actually from Seattle because the tidal range is a little higher, so it comes out really nice. But these are the average monthly high and low tides. These are the averages of those high and low tides. And this is the signal in that 18.6-year record. So it's very much a sine wave. And you can see at some points in the 2-decade signal, we have higher average water levels, and then at other periods we have lower average water levels. And so if you wanted to predict when you'd have maybe higher coastal flooding for the next couple of years, you could look at this underlying 18.6-year signal and say, oh yeah, this is a really bad couple of years for us. We're going to have to be worried about the weather from this 5 or 6 year period. And down here, maybe it's not so bad. But that signal's in there and has to be teased out of the data. This 18.6-year period is what's known as a tidal epoch. And basically, once you have that 18 years or 20 years of data, you can begin to average all your lower low tides of the day, all of your higher high tides, and you start to create what they call tidal dams. So tides typically, there's one lower tide, a lower low tide, and a low tide. So one's a little bit lower than the other, and the same with high tide. And so all these are used to determine what tidal range we should expect at any given location and what the mean sea level should be, which is the average of all the tides. So there becomes our mean sea level record. And if we compare mean sea level over time between these 20-year epochs, we begin to see in the record that sure enough, mean sea level is rising. And so that's based on those 20-year averages. And so that's where the tide gauge record becomes a really key component in understanding how sea level has been responding to this added heating of the ocean over time. Here, this is a figure from this. This is Atlantic City. I think I have one for Sandy Hook. So this is Atlantic City. Atlantic City again has this century-long record. These are the variations in monthly mean sea level relative to the current tidal epoch, which is I think it's from 1982 to 2001, something like that. And if we just look at the trend line through those monthly means, just like Matt showed us, we're seeing something around 4.16 millimeters per year of sea level rise, which is over the entire record is equivalent to that 1.4 feet, right? We talked about it. So 1.4 feet in a century. And here, this is the battery, same kind of analysis. It's about 2.9 millimeters per year at the battery. Sandy Hook is 4.17, and then Cape May is 4.84. So we notice right away that sea level isn't changing constantly everywhere, right? It varies by location. So there's a localized effect in how the sea level varies. Matter of fact, one of the highest areas in the East Coast is Ocean City, Maryland, which is around 6 millimeters per year. And notice I'm using the term relative sea level rise. Now, I've ruined my thunder because we've already explained, but that's because, again, it's these two components, right? The land is subsiding at the gauge location. The gauges are attached to piers and the land, so they're sinking with the land, and the mean sea level is rising due to eustatic sea level rise, or expansion of the ocean. So this is another, you can find these sea level rise projection plots from every agency. I think this is, I thought this was, no, maybe it's EPA. But again, the global sea level rise projections depend on the emission scenarios that we just talked about. But I'm more interested in what's going to happen in, say, the next 30, 40 years, because that's kind of what we're, as an engineer, designing things 40 to 50 years out from now. And so I want to just look at what may be happening between 2022 and 2050. And so when we look at that, we look at this little block, we see that all these projections are almost exactly the same. Maybe there's a little bit of variation at 2050. But for the most part, over the next 3 decades, we can expect similar trends to what we've been seeing in the data, at least over the last 30 years or so, because it is true that since about the mid-1990s, we've been seeing an acceleration in that sea level rise rate year to year. So what does that look like for New Jersey? So Rutgers University actually convened an expert panel in 2016 and then again in 2019 to take a look at all the different variables that are changing sea level locally here in New Jersey. And they came up with a projection. And their table is a little different, but it's giving the same information that we just looked at. And that is a varying range of sea levels depending on what the emission pathway we are moving towards plays out. And so at the low end, we have the low emission scenarios. So we have a greater than 95% chance of seeing these sea levels, that I'm going to talk about in a second. Here is the intermediate emission scenario, 50% chance. And then here are the extreme scenarios, the full on no change in emissions, 2 degree plus warming of the atmosphere in this century. And so notice that between 2030 and 2050, we have one number here. And so let's just look at the intermediate range. By 2030, we expect water levels to rise about 0.8 feet in New Jersey. And then by 2050, 1.4 feet. Right. And then when we get farther out, when we get to the point where the curves diverge out here, we have less confidence, like we just discussed. So now the panel's giving us a range based on the emission scenario that we are thinking that we're going to go down in the future. But here, I'm just focusing in on these next 30 years because they're pretty concrete numbers. There's no ranges provided here in the table, just a set number. No, I might have had it on another slide, but the reason this is one number is because we just learned that over 90% of all the heat, that has heating that has occurred on Earth has been absorbed by the ocean. The ocean is on a runaway train right now, and it's going to continue to expand for the foreseeable future at the same rates, because we've put so much heat into it that it can't change until after 2050. And that's when we have to think about what our confidence is in the future. So what are the impacts locally? As these sea levels continue to rise, we should expect to see more days of nuisance tidal flooding or sunny day flooding. So I'll talk a little bit about that. We should expect that when we have heavy rainfall events in our low-lying coastal areas at high tide, that we'll see more flooding. And then we should see more severe coastal storm surge impacts moving forward into the future. So nuisance tide or sunny day tidal flooding, this is, if you go down to the barrier islands or if you live close to the coast, one day you wake up and there's water in your street and it hasn't rained. This is the tide coming up through the storm sewer systems, the stormwater systems, and flooding the streets, or coming across the bulkheads in some cases, or through holes in the bulkheads. I see them come in always. But it's a nuisance in the sense that you really don't want to drive your car through salt water, or maybe you can't get out of your driveway, or maybe you can't get out of your house if it's severe enough. NOAA defines nuisance flooding as an exceedance above mean higher high water, the higher high tides of the month. And it's locally, it varies locally, but for New Jersey, it's roughly almost 2 feet above mean higher high water, 1.8 feet. So that's kind of the threshold where we should expect nuisance flooding to occur. So what does that mean? I've converted. So this is, again, if we took that 20-year tidal epoch and averaged all the lowest tides of the day, all the low tides of the day, we would get elevations for each one of these tides. So the high tides being higher than the low tides, the mean tide being in the middle. And then luckily for us, they've actually put in what's known as the geodetic datum on the tide gauge, and that's the datum we use to measure ground elevations on Earth. So if I set the tidal datum to 0 at the 0 elevation of the land, I can then convert what mean higher high water should be on the gauge. So it should be about 2.4 feet above the ground level. And then nuisance flooding should begin at 4.2 feet above the ground level. And so I can, nice thing about the tidal data at Sandy Hook or anywhere that NOAA, they let you change the datum, so you can look at it any way you want. So here I've converted the datum to the geodetic datum, and these are the observations of water levels above the geodetic datum, and these are the thresholds. So here I'm locating how many times. It looks like 2 times in the month of October here. We had an exceedance of that nuisance flood threshold right now.
Twice in October,
October of,
twice in 1 month.
in this case.
Just making sure
Yes.
that's a lot.
Well, it gets worse some days. So what does that look like? Well, here we've looked at an area in Rumson, New Jersey, Oyster Bay. This is the Shrewsbury River, in southern Rumson. This is an intersection, a well-known intersection that floods at high tides. And it turns out that it intersections is about 4 feet above ground level, NADB 88. And so that location would be expected to flood during these nuisance tides of 4.2 feet. So NASA has done a wonderful thing for us. They've taken all their satellite data and the tide gauge and combined them to create a projection tool of the number of nuisance flood days per year you should expect into the future. And so this is for the Sandy Hook gauge. And these are the different emission pathways, low, intermediate, high. And I want you to look at this curve. Nothing straight about these curves. This is exponential and almost a bell in some sense. So as we move forward in time, the impacts become exponentially worse, right? And so if we were to just take a look at today, somewhere around 2022, we should expect on the intermediate to low projections, maybe 20 days or so of flooding at that location, up to maybe 50 in the high range, right? And so by 2050 out here, just look at this low range, we're up around 75 days that intersection floods, right? Unless they change the intersection. So we're looking at, just over the next 3 decades, somewhere going from 25 to 75 days per year of flooding of the intersection. Right? And then as you get farther and farther out, you get almost every day, especially on the intermediate high and high scenarios, every day the street will flood. There's some places in Annapolis that it happens every spring high tide right now, especially around the Naval Academy. So what about rain and tidal flooding? So what happens if it rains during one of those already nuisance tidal flooding events? Well, as part of my work at the Sea Grant Consortium as a resilience specialist, we've been working with the community in Ocean City, New Jersey, to see exactly what that looks like, right? So we've been looking at how many days per year do you get nuisance tidal flooding, how many days do you get combined rainfall and flooding, how severe is it, what can we expect based on the data we're collecting. The Citizen Science Project, in the sense that we've given them a phone app to collect the data with, and they have rain gauges located around the town that they look at. We started this, let's say, in 2018, so we have about 3 years of data, a little bit more. And so what we can get from the data are everyone that gives us a report through the cell phone gives us a picture, it's geo-referenced at a location, gives us a time and date stamp. And we can go back, there's actually a tide gauge right back here on the bay. We can go grab the tide data and see what the tidal elevations were relative to street flooding locations at that time. And again, they're collecting very simplistic, is the NOAA rain gauge that we have given a number of people in town to collect rainfall. Here's one of the data points. And then we also have flood references on a number of telephone poles, which give the what NOAA, the Weather Service, has determined to be the low, moderate, and major flood levels. You can't see it there, but these little reflective bands, so that if we do get a significant flood, they can actually take a picture of the pole, see where the flood level is. So what are we finding? So let's watch that a little bit. But of the data collected, 121 events as of last April. I haven't really updated the data since then. We had seen that 50% of all flood events have occurred in this nuisance flood level. And we're defining nuisance not as 2.4, but 2.24 feet. And I'll tell you why in a second. The minor flood level for this location is 3.24 feet, and about 45% of the events fall within that range. And then we've caught a couple moderate storm events since 2018. That's about 5% of the data. So we're finding that this should be a 2. Sorry, minor flooding for this area starts at 2. Oh no, minor flooding is set by the National Weather Service is 3.24 feet. But we see, especially during rainfall events, a lot of flooding a foot lower than that. And then right now, we're averaging 45 flood events per year. For this region, the nuisance flood events should be around 20 to 24 right now, based on NOAA's analysis. So we're finding that NOAA's flood thresholds for sunny day or nuisance flooding are severely underestimating the flood hazard, at least nuisance flood hazard. And then when we look at when did rain occur at any of these events, 72% of the time nuisance flooding was associated with rain, 46% with minor flooding. And what's interesting is here's that nuisance flood threshold. This is the tidal elevation relative to the land on the left. On the bottom is the 24-hour rainfall. It doesn't matter how much it rains as long as the tide is above the threshold. So once it gets above this tidal elevation and it rains, we should expect flooding. And then lastly, I just want to talk about storms quickly. Late, right? So again, we did this for Ocean City as part of their project. Here's the main access road into the city. It's about 3 to 4 feet above the geodetic datum. This is a storm event that occurred back in 2018, maybe 2017, where we had flooding of the boulevard through about 5 or 6, maybe 7 tidal cycles during a March storm. And so just looking at extrapolating sea level rise over, this is from 2018 to 2074 for some reason, but we chose those numbers. The blue was the observed tide in 2018. The red would be the predicted tide when, if that same storm occurred in 2074. I should point out that this is near flood, minor flood, and then moderate flood. Up here, we had three moderate flood levels during that storm in 2018. If sea level rise only changed, we would see that moderate flooding would have been exceeded 4 times, and severe flooding or major flooding 1 time in that storm event, 7 times for moderate. So we can see just sea level alone increases the number and severity of flooding for any particular event that's occurred in the past. We can look at the entire water level record over some period. This is the 20-year period from Atlantic City. This is Sandy out here, the highest point. And we could say, this is not a good assumption, we could say that the storms will stay the same into the future. But the only thing that would change is sea level rise. And if we do that, we can take that data and we can say, hey, how many times has the tide exceeded mean sea level at that gauge over this 20-year period of record? And so this is the amplitude of the tide. This is mean sea level at 0. Almost all tides exceed mean sea level. And then there's some cases where it's 1 feet higher than mean sea level, 2 feet, 4 feet, etc. And so we look at where most of these observations are falling is in the tidal range at the gauge. But then out here at the higher water levels, we're seeing the coastal storm impacts on water level at the gauge. So I can superimpose the elevation of that roadway right here, 3.4 feet. And we see that it really should only flood in the most significant storm events outside the flood, outside the tidal range. And so in 2018, when we looked at this analysis, we saw about 24 events a year should it flood the road, right? If we add sea level rise to that same tide graph, number of high tides above the mean sea level, we see that almost all tides occur above mean sea level and then less frequent out as the tide goes higher above mean sea level. This is the 2018 data. This is the projected sea level at 2030, and this is 2050. And these are the higher ranges, which I will look at. But here's the flood threshold for Roosevelt Boulevard again. Here's 2018, 24 flood events per year. By 2030, same storms characteristics, we should see almost 130 events per year. And then by 2050, 300 events per year. So that's almost every other high tide flooding the boulevard. So just in conclusion, just quickly, we can see from the record, mean sea level is definitely rising directly due to the heating of the earth and global warming. Sea levels will continue to rise due to the sustained response of the ocean to the warming, just because it's heated already. Relative sea level changes and subsidence will continue to combine to create more and more impactful storms around here. And then we should expect a large increase in the number of nuisance flood events. We don't really understand combined rainfall tidal flooding, but that should also increase. And then storm surges are certainly predicted to be more severe and more impactful moving forward for the next 3 decades. That's it.
And now we move to the panel portion of our program where Dr. McKeever will maybe give a remark or two at the beginning, and I may ask a question and I'll open the floor for questions. Dr. McKeever is a lecturer in economics and finance real estate at Monmouth University's Kislak Real Estate Institute. She currently teaches principles of finance and money, credit, and financial institutions, and she directs the Kislak Real Estate Institute. I presume she's going to talk to us a little bit about impacts on real estate of the information that we just learned. Dr. McKeever has more than 15 years of experience in the commercial real estate finance industry, and she worked for Berkadia Commercial Mortgages Loan Origination Group. And for those of you who know anything about Berkshire Hathaway, it's a joint venture between them and the Jefferies Financial Group. Her research interests include commercial real estate, valuation, mixed-use properties, city growth, and behavioral real estate. Dr. McKeever also has twin bachelor's degrees, but in economics and psychology from UC San Diego. And she earned her MBA with a concentration in real estate here at Monmouth and her doctor's in business administration from Temple. So Dr. McKeever, Dr. Herrington, and Professor Paccico.
You can start with so when we're looking at the presentation, the information given to us by Dr. Herrington, it's kind of difficult, right, to say what's going to happen exactly. But what we know with certainty is over the next 20 to 30 years, probably no change, and perhaps that's why municipalities and people can put this in the back burner. But as you can see, in the next 30 to 50 to 100 years, are we going to be able to use the real estate that's along our coastal communities, right? And so the first question or two issues come to my mind is, can we use it, right? And then number two, if we're talking about residential or even commercial real estate, then we have to look at insurance, right? So on one hand, can we build, right? There are workarounds that I think municipalities look into, right? So the net effect of sea level rise is flooding. So how do we protect against flooding, sea walls, flood barriers, ordinances that say you have to build above certain height. Those are some potential workarounds. But you know, the one thing I did think about was driveways, right? You can build high, but then how do you get to your house, right? So that's an interesting question. I was just reading a study that said, potential obsolescence of real estate is in the order of $34 billion with respect to coastal flooding as it relates to sea level rise. So it's interesting to see where this is going to go. I think in the long run, insurance is going to be a very big issue to the point where those that can afford private insurance potentially could be some of the only people that live on the coastal communities. Because that's what it's gonna come down to is ensuring your property, residential or commercial, so that you can withstand the impacts of extreme weather. But then that can also go to, are people going to want to deal with that, right? You can insure it, but do you really want every 2 days or 3 days to worry about flooding in your home, getting to your driveway, et cetera? And so I think that's going to be a real challenge going forward in New Jersey specifically, and not just coastal communities, right? You know, you have all these tributaries that run through Somerset. It always floods in Somerset County. So it's interesting to see where it's going to go.
One of the things that occurs to me in the presentations given that seems to have applications for the coast is the rates of change and also the biology of sea level rise. Many of our communities rely on wetlands and sand dunes. And at 4 millimeters of sea level rise, most wetlands can barely rebuild themselves. At more than 4 millimeters of sea level rise, the wetlands begin to die. And what's going to be the real estate impact of having rotting wetlands or losing them, those barrier protections?
Well, the one saving grace, whether you want to see it this way or not, is wetlands technically cannot be built upon. So there's a saving grace there. But as far as the deterioration of wetlands, I think that's something that's out of my area.
It's certainly a concern. Like you mentioned, that 4 millimeters per year seems to be about the rate that they can continue to keep up the sea level rise. And there is a lot of research going on in the state of New Jersey now on how to create adaptations to help lift those marshes up over time. And mainly that's using the dredge material we're taking out of the channels we're dredging for navigation and repurposing them. But it's just one part of the puzzle, right? The marshes are supposed to be underwater a certain amount of time per year to survive. So during storm events, they do reduce some flooding and wave action, but won't completely protect communities from the flood impacts, right? So they are valuable, but probably not going to be as effective as some other methods of reducing our flood exposure.
And that's one thing I forgot to mention was, you know, we're running out of room to build. So this idea of impervious coverage, right? We can't continue to build on all available land because then the water has nowhere to go. So then we have to be smart about developing and redeveloping existing land. So that was just one thought that I wrote in my notes.
Are we opening to questions?
I think we are opening to questions.
I have a twofold question because of course I do.
Okay.
My first one is there any data on the breakdown between how much of the billions of dollars of infrastructure and building on the coasts by, let's just say class, like who owns which pieces of land? Because like you said, people who live on the coasts are only going to be people who might be able to afford private insurance. But those same people are the people who can afford domestic labor. So like it's not true. There will be people living on the coasts, but they'll be uninsured. And I'm a little curious about the economic impacts on people who will live uninsured and how many people there are.
So I don't think there is like a database that exists, but you can search up and, you know, it's things that we're working on at the Real Estate Institute to figure out, you know, how can we data that best serves our community so we can figure out who owns what. Everything is public record.
Right.
But I don't know the breakdown. So, but
part two, I think, of that question is, how is that going to impact the economic community currently? I think it will. You know, the fabric of our community are for people who have been there for a very long time. And I think they're going to have to make a decision to remain uninsured, but then the economic consequences of that is you have to, you know, repair any damage or casualty that occurs to your property without the benefit of insurance. So that's, you know,
Just
you're not
continuing in that
exactly,
conversation, yeah.
you're not really going to get away from having to rebuild or repair damage caused by flood.
On that note, in terms of Florida, it's almost 15% of the people don't have insurance.
That's right.
Now, that's because their historic cost is low and they can't afford the upcharge. That being said, when there's damage, they still have to bring their homes in many cases up to
Code. That's right.
which is financially impossible.
And then what happens? People sell, right? Who buys, right? Either secondary home owners or investors who want to, you know, rent out the property, just like we have here at the Jersey Shore.
Aren't they starting Blue Acres programs where they buy homes and?
Yeah, I think there are programs out there. I'm not too familiar with them, but I'm pretty sure they do exist.
Yes.
Yeah.
Because sometimes you gotta throw in the towel, you know, like it's enough already. How many times can you get flooded?
Well, exactly. And do you really want to go through that every, you know, whenever there's a flood?
I just think though, but realistically, some people, that's their home, and that all of their financial assets are invested in that home. So, well, if it's a second home, you could say, okay, I'm just gonna not go to my second home, but it's not, you know, there's other people who don't have that much.
Right.
Well, I was thinking like anything that makes sense.
Professor Myers, you had a question.
You did. I was wondering how you see this playing out for emergency services. When I was in Tampa, we had many blocks. There was any veteran that you just couldn't get down, right? And they were blocked out, cordoned off. And so where do we see this for the Jersey Shore as far as emergency services? Ambulance getting in, fire troops getting in. Are we now gonna have boat services for these things? Like, do you foresee that being an eventuality that they'll have to consider?
Yeah, I think so. I mean, not both, so that's a little dramatic perhaps, but I think looking at emergency services as a risk. So if you look at the barrier islands now, Long Beach Island, for example, the low point is the central boulevard that runs up and down the island. That's what floods every time there's one of these tidal flood events. You compound it with rain, you compound it with sea level rise. Right now, you know, you get a couple inches of flooding and then kind of just takes over the intersection. Perhaps you can drive through it, but looking at 2050, perhaps, and you add another foot of sea level rise, and if there's any sort of storm that causes an emergency situation, you could absolutely run into a situation where you can't get not just emergency services up and down the island. Typically, fire trucks, ambulances are a little more robust, but you could have people trapped on the island because they can't get cars out. You know, what is it? A couple feet of water, moving water is enough to push around an SUV. So this moving water has a lot of force behind it. If you think about a storm like Sandy, where the entire barrier island of Long Beach Island was underwater, the ocean and the bay met in the middle, you can't drive through that. So you could definitely end up in a situation where emergency services are stressed.
President Hoffman, I have a question about your map where you have the measuring devices. I noticed there's some in the Great Lakes. What are the impacts there? I understood that the levels were down in the Great Lakes.
They may have been this year, they have been abnormally high, so they're really driven by precipitation events more than expansion, although there's an expansion component, they heat as well, so. But lake level variations have been correlated much more closely to rainfall, and so and what's problematic for them is when they get high stands of lake waters, they see erosion impacts and destruction of property for a couple of years in a row, and then maybe it goes down and they have a couple of years where there's no problem at all. So they're kind of unpredictable events in some.
And just to be crystal clear, the ice sheet dynamics that we were talking about don't play a role in the Great Lakes. They're hydrologically disassociated from the ocean basin. So the thermal expansion plays a role, especially when you consider that there's a lot less volume, so the water is able to heat up faster. But those ice sheet dynamics, that water doesn't make it into the lakes.
Thank you.
Eleanor?
I wanted to comment on the costs and benefits of the beach management, including the opportunity costs of bringing them elsewhere. Also including the cost of carbon dioxide that goes up in the atmosphere, there was a factor in the ground up there.
So I'll address that a little bit. So how do I start? So a couple of things go into the decision to rebuild our beaches, and one is they are very effective at mitigating coastal storm damage impacts when we have big storms like Sandy or big nor'easters. If the beaches and dunes are high and wide enough, they prevent almost all damage except maybe to the first row of homes. So we've seen their value. New Jersey invests $25 million per year into maintaining their beaches. And we know that just from tourism revenue alone, it's almost a $20 billion a year business around coastal tourism. So for New Jersey, it makes a lot of sense to continue to invest in it today. Is it sustainable, 50, 60, 70 years from now? That's the question, because as sea levels rise, we also expect increased frequency in storms. So, but right now, I think from New Jersey's perspective, it makes a lot of sense. That may not always be the case, but it's certainly cost benefit wise right now a right for New Jersey.
Can you repeat the cost factor to the state of New Jersey, 25 million, what did you say?
So we put aside $25 million per year to invest in beach road projects with the US government. And so almost all of our coast is under federal shore protection projects, which is typically a cost share now, 50% federal dollars, 50% state dollars. So in that sense, it's even a bigger benefit for us because we're only paying part of the total cost. The interest from the federal government is reduced payouts in flood insurance and presidentially declared disaster funding. So that's why the federal government's interested in building beaches.
There's a question from the Zoom audience about interactive maps and charts of the New Jersey coastline showing the effect of high tides. I'm presuming there are, and then we can provide it in a moment.
Yeah, so Rutgers University has a web page called NJ Adapt. And there they have tools where you can look at different sea level elevations relative to land, what should be flooded. They also, I think, allow you to put storm events in there. So there's a lot of information about, just looking at what may be flooded in the future.
So a search NJ Adapt at Rutgers. Would that work?
Or just NJ Adapt should find it.
Okay, perfect. And I guess Professor Schreiber.
I think this is maybe a whimsical thought, because I think I already sense the answer when you say, but you talked about rise in sea level. You could be talking about where the coastline goes then, with a certain amount of sea level rise, but it's never that clear because of storms, things surge in and make a mess. Is anybody looking at it that way? We're more than a foot above sea level here, so everybody look at it. Is that useful at all?
Yeah, there's compounding dynamics, right? There's the sea level rise, the static rise that when we were talking about looking ahead to the end of the century, as high as 8 feet. You lose the barrier islands on the Jersey Shore at 8 feet. And you lose significant portions of the coastal communities on the bays. But really what you're going to see before that, like you alluded to, is impact from surge just continuously compound in these neighborhoods. And so long before the sea level actually rises above those islands and claws that back, you'll just see, as Tom was showing, intersections that flood daily, right? And when there's one of these extreme tidal events or rainfall, they flood severely daily. And so that's it. There's two very different thoughts there. But yes, you can look at it just strictly from a static water level and say there's a chance that, you know, towards the latter half of the century, we start to just lose significant portions of land.
Yeah, people will find their living untenable before that happens. Yeah, I was really appreciated the comment about, okay, could we build up higher? And I see that because I live not down low, but in the high part of the islands. I see all these houses being jacked up, and people aren't going to be able to get to them or get out of them. And I drive up Ocean Avenue every day with these combinations that we go by. It's kind of a shame. Now I just thought that's
And, to that point, Bill, and to the question about access and emergency services. So when I work with my community in Ocean City and I talk to them, and we know they've been collecting their own data, they know what's happening, right? And I go to a public meeting and I asked them, I said, so at what point does this become untenable and you're going to sell your home? And they look at me and say, I'll never sell this home. So that goes to the sense of place and value, right? So at what point does the sense of place?
politics and political reality. Not because one brain's going to exist for all countries. I have an energy.
Another question that occurs to me, which you could all three contribute to in different ways, is what about municipal contributions specifically? The gentleman who will never sell his house, but what happens when the town says, we refuse to send an ambulance to your house? We can't support it anymore. The road is in too bad condition. It's likely to be underwater, all the time. At what point do you have people suing their municipality for services? And what is that? And how does that play out socially?
I can tell you it's happened and it's happening.
Yeah, I was gonna say.
And when I think there's a couple cases in Long Island on the sound side where the road kept getting washed out, so the municipality decided they were not going to maintain the road or utilities, and they lost in court because they're supposed to provide everybody services.
They're obligated, right?
Sir.
And a comment and a question, but to that point, there's insurance companies today that are refusing to insure coastal homes. We have a friend who just today, State Farm a couple of years ago said, we're out of the coastal insurance business. They had gotten another company who just this week told them, we're not insured, we're reducing our portfolio. So these very sophisticated analytical organizations called insurance companies are making financial bets today in New Jersey and reducing their exposure. And I think talking about insurance, the other thing is the National Flood Insurance Program.
Yep.
How do you think the federal government and that program begins to impact these couple of issues? So this issue, it pulls on the communities, but the federal government has historically played a big role by creating this financial incentive to the National Flood Insurance Program.
So I think, first of all, the NFIP doesn't, we're recorded, but it's okay, a poor job of providing coverage, right? The limits for both residential and commercial are extremely low.
Okay.
That's the first thing. The second thing is they the NFIP and FEMA cannot update risk maps fast enough to account for what we just saw right there. So that's an issue. So you have insurance companies who have their own models that, you know, what we've seen. And they offer coverage with a premium that is much more expensive than your current retail coverage. So like the warehouse coverage that flood is kind of covered under, in addition to your home insurance, it's extremely much more expensive than, you know, if we account for the modeling that most private insurance labels use.
I also had my insurance pulled a few weeks ago.
Is there statistics on that? Is there? Is that trend going with the sea level rise? Is it increasing or accelerating?
Yeah, no,
Well,
that's
this way, the actuaries are not denials.
Right.
They have very good risk assessment.
oh, it's 100% true. And there's a website, I think it's firststreet.org, where you can actually see your flood risk. And it incorporates modeling such as sea level rise, but also new roads, new developments, right? Because that actually changes the way that water floods and pools and whatnot. So
I decided not to ask that information. I have a question that is sort of about the interplay between your profession and your knowledge. I noticed in one of Dr. Harrington's slides that there was like in the table showing sea level rise by confidence for 2030 and 2050, rise in the 50% confidence sort of section, I don't know what to call it, was 1.4 feet by 2050. And in the 0.5% confidence but high risk scenario, it was 1.3 feet by 2030.
Oh.
And I'm kind of wondering, is it common in your field to use pieces of data that match up really closely like that to encourage people to build more resilient infrastructure sooner? Because if you were to build something that was resilient to 1.4 feet by 2030, there's a good chance that it will continue to be resilient until 2050. And it might be more insurable because of that.
well, I think to the buildable portion of it, I do think that when developers and municipalities are looking to build any new structure or replace an existing structure, they have to account for extreme weather now. And I think that's something in the forefront of developers' minds currently. But I don't know to what extent, you know, I think everyone understands that this is an issue, but I don't know how far and how much they're applying this knowledge to actual development currently.
Yeah, we talk about, when I work with municipalities, we talk about no lose investments that are going to add resilience now and will be worthwhile over a certain period of time. And so if we're building an infrastructure system with a useful life of 30 years, we look at, okay, what's the minimum sort of investment? Because a lot of times money is an issue. What's the minimum investment that's, you know, worthwhile for that time period? And what investments, you know, are essentially no lose. The community is going to see that benefit, because it's often quite difficult to sell communities on what really are extremely expensive infrastructure improvements to keep out the water. Everybody's so focused on maintaining the current shoreline, and when you look 30, 40, 50 years out, that can be extremely expensive.
Exactly.
Speaking of maintaining the current shoreline, there's a question from the audience, which says, the only way we're addressing ocean rights is through nature management. And basically, when do we try something else and when should this happen? For you engineers, I believe that's a question.
Yeah, so I can start by just referencing the number that Dr. Herrington said, which was, New Jersey spends 25 million a year on beach replenishment. Any sort of what we call gray infrastructure improvements that would do something similar would be 10 times that cost, upwards of potentially 100 times that cost, depending on the stretch of shoreline that you're protecting. So if you're looking to maintain the current shoreline and you want to look at, these what we call gray infrastructure, hard infrastructure, seawalls and flood barriers, that gets extremely expensive. And the other option then is retreat. And that's not a word that anybody wants to hear, especially I work with municipalities where retreat is not an option within the municipality. So they don't want to hear anything about, essentially giving up their town.
Yeah, I would agree. I think, two things. One is that after Sandy, I think the entire field of science, engineering, social sciences looked at the coast holistically and said it's not just the beaches that need to be maintained, but we also need to think about our bay shorelines, investing in restoring our marshes or maintaining marshes. So there was a real systems look at it. Even the Army Corps and their studies, even though they're proposing storm surge barriers, still looked at the entire system as a way to maintain resilience from storm impacts. And so that's certainly helpful. I think one of the challenges is if we're not maintaining, at least in the next 30 years, our coastlines, then the alternative is that it will erode away. We know that. The properties become more vulnerable. And then you run into a whole series of private property issues, right? Any homeowner will want to protect his investment, and they'll put in the bulkhead, they'll put in the seawall, they'll put in, and we've seen this happen in places in New Jersey in the past. So it's a question of, who's going to hold the line and how, I think.
Do you foresee the government in the future creating policy to not rebuild a barrier island? Not the island itself, but structures. Because to your point, it is private and we do subsidize flood insurance. So it's a constant, we know it's constant, we know it happens. Which now looking, this is the second or third inlet that we rebuilt.
Right.
But we know it happens. And I know it's private, but we have buyout programs. Blue acres. And eventually that's on the table for a lot of barrier islands. Do you see government creating policy to say, I'm sorry, you can stay as long as you want, but
I
when
think
it's
that
done, it's done.
personally, my opinion, I think that gets very tough because the way that municipal land use law works in New Jersey, the municipality has say over what is built in the municipality. So it's
Right.
going to be very hard for them to reach in over county, in over the municipality to say you can or cannot build here, right? With the exception of NJDEP CAFRA permitting and wetlands, things of that nature. I think it'll be very hard to get the state to override municipal ordinance on what to build in a municipality.
But I know with buyouts, if something happens, if I'm not going to insure you because the federal government insures it, and you have to carry flood insurance on a mortgage. They say we're not giving it to you, then you can't stay. Unless you have a mortgage.
Unless you come out of pocket for it.
Right.
Yeah, I'll add, I just don't see the political will in Congress to do that right now. Like, I think
That I would agree.
But yeah, the regulatory tools are how they're attacking it now. National Flood Insurance Program last year instituted new rules that change the way they figure out your flood risk and your insurance cost. And they're trying to get over the next 5 years or so, increases in insurance rates in the flood insurance program so that the full actual value of your home is taken into account. Because we subsidize a lot of the homes.
Right, isn't the back value 250?
Yeah, the payout's 250,
Right.
but what you're paying for your insurance
Well, that's.
is going to increase,
Economic.
right? And so that's a tool, right? So that becomes a financial tool to make people think twice about building here or investing here.
Because I know New York State after Sandy told sections of like Staten Island and Brooklyn will buy everything out, but
Right.
everyone has to go.
Yeah.
Not one and then 5 houses, you get them all.
Yeah, and that's a cost thing too, right? So we do have a really robust Blue Acres program. It's a model for the country in New Jersey. But it's, funded at 300 million right now, mainly thanks to the last storm events that occurred a couple years ago. And when you look at our coastal properties, how many homes can you buy with that amount of money to make an impact, right? So in the case of Staten Island, they had federal money coming in from disaster relief that they could put towards this with a willing community. They all agreed to it, right? So I think there's a lot of social issues, economic issues that need to be figured out when these kind of buyout programs work, right?
Right. Because didn't Mallow argue about just the big standard from
Yes, they did. It was a takings case, right? Eminent domain easement.
Yeah.
Maybe 2 more questions?
Sure, I mean, I don't understand when we do the beach replenishment, why it isn't multi-tiered where you have to build dunes also as a secondary protection besides the replenishment. And then the third would be dredging the tidal ponds, which, well, they're now lakes, but they were tidal ponds 300 years ago, which are now basically retention basins for all the construction west of that site. So, some of those lakes now, I mean, Wreck Pond and Spring Lake, Como Lake and Spring Lake, Sylvan Lake, Silver Lake, they're all 3 feet high. And, they basically don't function properly as a retention basin. So, I mean, I'm looking for a multi-tiered level. We're gonna do the beach, let's follow up with the other items also.
Yeah, that's, I can tell you why there's no dune in Monmouth County, and that's when these projects go back to the 50s when they were designed, and so in Monmouth County, the shore protection project was classified as an erosion control project and not storm protection, so that's why it has no dune. But after Sandy, the Corps was told to go back and look at it and see if a dune was necessary. I don't think they've done that, but they were supposed to do it, and they may still do it. So that's one quick answer there. But the other thing, yes, so Representative Smith has asked that question 100 times. Why aren't we connecting the coastal lakes to the shore protection projects that the pipes go through? And they have yet to commit to doing anything in the lakes. So it's out there, and we hope that in the future that it will be more of a system, thought process rather than let's just put one component.
And the dune part of it is probably like, no, it's my view, I don't want to do that. How that works.
It could be, yes, it has been. I will say, some of these projects they started in the 90s. And so as the building stock has changed over the 3 decades or so, people have gone from duplexes that are top bottoms to side by side.
Mhm.
And so we've seen the real estate market adjust for the loss of views. It's quite interesting.
Yeah.
Yeah.
Let me have a little on that. A lot of it is the philosophy of the Corps of engineers and the geomorphology of New Jersey. So the Corps divides New Jersey roughly, and the Army Corps from Aswan Inlet north to New York, and from Aswan Inlet south is Philadelphia, which is pretty much the same kind of divide of where the barrier island started and where the bluff started. So to the north, which is the Army Corps, you see Long Branch is a bluff area, and dunes really weren't that important. And then north of there was this massive seawall that built in the 60s. And south of there, the barrier island. So the Philadelphia Corps is very adamant about building dunes into their program, to provide that elevation relief. Whereas the Army Corps, New York district was not so much for doing already elevation relief because of the bluffs and islands. So it was really a lot of it was a difference in philosophy in response to the geography of the land. So it's pretty interesting at least how that developed.
It's 8 o'clock. And we had one question from the audience, and we have a question where I believe the answer is political will from our studio audience. Which goes, if sea level rise is inevitable, at what point do we need to address it with something more useful than piles of sand? It is certain that some areas will be impossible to protect. We're already in a 3-year replenishment cycle. What's the tipping point? I believe that the answer to that question is beyond the scope of our expertise in this room. Do you have a question that is within the expertise in this room?
Yeah, I understand. Important for it to be very good. But I don't hear anything addressing. Well, kind of that short term thinking, 30, 50 years down the road for human economy. I guess I would have liked to have heard a little bit more.
About solutions?
Pardon?
We'll be doing climate solutions later on in the teaching. That we can't solve all the sea level problems in an hour and a half. Although we would like to. So I will thank you for coming. I expect that the speakers would be willing to take a question or two if you have a private question. And I'm sorry for the studio audience. Thank you very much for your attendance, and stay tuned for more. The climate crisis will continue on Thursday with a Zoom event about climate change and reptiles, specifically in the UK, but also referring to terrapins. And we have another event next Monday in the Great Hall on the intersection of climate change and art. Ooh.